This video demo shows how to build molecular systems containing more than one type of protein and no membrane or periodic components. Before using Multicomponent Assembler, you should already have a CHARMM-formatted PSF and CRD file for each distinct component in your system. Usually, these files can be generated by PDB Reader, Glycan Reader and Modeler, and Ligand Reader and Modeler. This video assumes that you are already familiar with these CHARMM-GUI modules. If you are not, you should first watch the video demos for those modules before continuing. For molecules already described in the CHARMM force field, Multicomponent Assembler only requires the CHARMM PSF and CRD files of each component. Otherwise, any additional topologies and parameters must be included. In this video, we will show how to assemble systems in the first case. Our first system will contain three types of proteins that are already well described by the CHARMM force field: Ubiquitin, 1UBQ, Filin, 1VII, and the B1 domain of streptococcal protein G, 3GB1. Previous studies have used these proteins to examine the effects of protein crowding at different protein concentrations. To begin, we first build one copy of each protein using PDB Reader to obtain the PSF and CRD files needed by Multicomponent Assembler. To build Ubiquitin, go to PDB Reader, type 1UBQ, and click Next. For molecules containing crystal water, we can choose whether to include the water in our model. Multicomponent Assembler can handle models containing water, so feel free to include the water chains if the initial position of water is important for your study, then click Next. If we want to make amino acid substitutions or other modifications, this is where we would do it, but in this demo we will simply click Next to obtain the PSF and CRD files of the unmodified ubiquitin structure. Because ubiquitin is a small protein, it should take less than a minute for PDB Reader to finish processing this structure. However, if your system contains many large proteins, you may want to build each one in a separate window and use the Job IDs page in your user profile to check the status of each protein. While we wait for 1UBQ to finish, we'll build the structures of the other two proteins. Download each built protein and extract their project archives. Because none of these proteins required any additional topologies or parameters, we only need to keep the PSF and CRD files. Multicomponent Assembler uses the file name to distinguish components from each other, so you should rename the PSF and CRD files to something descriptive. Make sure that the PSF and CRD files use the same name before the file extension. Now that we have one copy of each protein we want to include in our system, we can upload these molecules to Multicomponent Assembler. Simply drag and drop the PSF and CRD pairs into the file upload area and click Next. After Multicomponent Assembler uploads the files to the CHARMM-GUI server, it calculates a few important details about each component, including the molecular length, volume, charge, and number of residues. The Step 1 page shows options to control the system size and amount of each component. While system setup is easiest if you already know the target system size and number of molecules, Multicomponent Assembler provides volume fraction and component ratio options to guide you through selecting an appropriate system size and composition. If we click the Calculate System Size button with the default options, we are shown the calculated volume fraction and recommendations for the minimum side and maximum volume fraction. Multicomponent Assembler calculates the volume fraction as the sum of component volumes divided by the total system size. The minimum recommended side length is chosen by adding the standard non-bond cutoff distance of 12 angstroms to the length of the largest component to ensure that no component interacts with its own image. The maximum recommended volume fraction is calculated by assuming that the difference between the solvent accessible volume and molecular volume accounts for all empty space in the system. In most cases, packing a system above a 30% volume fraction is very difficult and may require some trial and error. If we instead know the target volume fraction and want to find the smallest box size that achieves this fraction, you can select the volume fraction size option. Enter the desired volume fraction and click the Calculate button again. Here we see that with one copy of each of our 3 components, a 10% volume fraction requires a side length around 59 angstroms. You can increase the number of copies of a particular component by entering the desired number in the Number of Components column, and click the Calculate button again to get a new size calculation. However, this requires that you know the exact number of each component that you want. If you instead know the ratio of components with respect to each other, you can use an approximate volume fraction and box length to find the system size that best matches the component ratio. For example, if we know that we want our 3 proteins in a 1 to 2 to 1 ratio, a 10% volume fraction, and a cube side length of at least 100 angstroms, then we can choose the Ratio of Components option. Enter 1, 2, and 1 in the component ratio columns. Enter 100 as the box length, 0.1 as the volume fraction, and click the Calculate button. Multicomponent Assembler will then calculate the system size and composition that best matches your settings and update the component count column. In this case, because we chose to approximate the box length and give an exact volume fraction, Multicomponent Assembler determined the box length closest to our approximation that has the desired volume fraction and component ratio. If the box length is too small or large, we can change the length approximation and recalculate. In the next video, we'll show what happens if we change the component types or choose membrane generation, but since we are not generating a membrane in this demo, we simply click Next to go to the Solvent Options page. Multicomponent Assembler then attempts to find a packing configuration that avoids collisions. Depending on the system size and density, it may take several minutes or hours to finish, so you should save your job ID or periodically check the status of your job on the Job IDs page of your user profile. If Multicomponent Assembler was able to find a reasonable packing configuration, it will show the Solvent Options page. Remember to check the packing results visually by clicking View Structure before proceeding. Notice that each solvated protein was given a random orientation. On this page, we can control the solvent composition. We can add ionic components by selecting a compound from the menu and clicking the Add button, and remove them by clicking the minus button. To add a compound not listed in the Simple Ion Types menu, check the More Ion Types option, and select a cation and anion. Each elemental ion type is categorized by its position in the periodic table. The list also includes most of the CHARMM force field's polyatomic ions that have fewer than 10 atoms. You can also select a different anion or cation in the compound list below. If you have more than one ionic compound, you should select which compound will be used to neutralize the system charge. If molecular packing results in a positive or negative system charge, ions from this selection will be used to neutralize the system, even if the concentration is set to 0. Finally, click the Calculate Solvent Composition button to get an estimate of the number of each solvent and ion molecule that will be generated. In a later demo, we will show how to adjust non-ionic solvent density or concentration, but for now, click the Next button to assemble the solvent and non-solvent components into one system. If solvent building and system assembly were successful, you should see a system size summary and periodic boundary condition options. Make sure to view the assembled structure by clicking View Structure. Note that it is normal for some components of our cubic system to cross the box boundaries, since the molecular system is modeled as a periodic system along each dimension. If you pay close attention, you will notice that every protruding protein has a corresponding cutout of water on the opposite side to make room for that protein's image in that direction. If the system looks correct, click Next to generate the PME grid and perform a short energy minimization. Input generation options are the same as in Solution Builder and Membrane Builder. When input generation finishes, click the Download button to download your system. To avoid naming conflicts in the segments of uploaded components, each component copy is given a unique name. To see how each component was renamed, you can look at the Rename Map text file. The general naming scheme uses 3 letters to distinguish uploaded components, and the following numbers to distinguish copies of the same component.